So up to now we have seen the generalized expression for the electric field and magnetic field for a Hertzian dipole. Then from that we drop the near field terms which are dropping faster than 1 by r, and we have found out what are the radiated electric field and what are the radiated magnetic field, and then we have found out what is the relationship between them. So this is the generalized expression for Hertzian dipole. Now let us consider a typical example for Hertzian dipole, practical example for Hertzian dipole. Why this is called Hertzian dipole? The first question is, why this is called Hertzian dipole? The reason is an explicit expression for the real value. As you know, when you call fields, if you are measuring the field or if you can measure any physical quantity, the quantity must be real. If it is imaginary or if it is complex, if it is imaginary you cannot measure it at all. If it is complex, then you can measure its real part. So the explicit expressions for the real valued electric field and magnetic fields for an oscillating z-directed dipole. Let us say the z-directed dipole has a dipole moment pt. It is oscillating, therefore it is if it is oscillating, it is varying with time, because oscillating means at t is equal to 0 the dipole will be at some position, both the charge at t is equal to maybe capital T by 4 or time period by 4, they will change their position. Capital T by 8 they will change their position. So then capital T they will change their position. That will happen. Therefore it is a function of time. So pt, let us write it as p z cap. Why z cap? Because the dipole is oriented along the z direction. So p into z cap, that gives you the direction. Then time variation, let us take it as cos omega t. Why we will take it as cos omega t? Now at t is equal to 0, this will be 1. Cos omega t is equal to 1 when t is equal to 0. So that is why we are considering it as cos omega t. That is, which means the dipoles exist at t is equal to 0. The separation is maximum between them. So QDL is the separation which is maximum separation between the dipoles, and when t omega t is equal to pi by 2, which means omega t is equal to pi by 2 means t is equal to pi by 2 omega. So in that case it is both the dipoles are at the center, so they will be 0. So pt will be 0. So pt will be between p and 0. That will be varying between p and 0. Therefore we have cos omega t variation. So this is this explicit expression. They were obtained historically. This is a historically important problem and history. In the history, they were obtained by James Clerk Maxwell. Then they were obtained by Henrik Hodge. Following James Clerk Maxwell or J.C. Maxwell or Maxwell, he predicted that electromagnetic fields exist. Right? He predicted the existence of electromagnetic field, E and H fields. Existence were predicted by Maxwell, but he could not prove that actually electromagnetic fields exist. They are a wave phenomenon and they are propagating. That could not be proved by Maxwell. Hodge did some experiments to prove that. Therefore, Henrik Hodge, he considered this problem first, and in 1889, whatever experiments he did and whatever conclusions he arrived, both the theory and conclusion and the experiment, they were written in the form of a book. Now it is called Electric Waves by Henrik Hodge. It is published by Dover Publication, New York, in 1962. It is a very interesting reading. You can read it. Get this book from Google Bookstore, so which is available for free at this website, the website I am giving you. And this is available in Google Books. This is the website in which this book is available. Electric Waves by Heinrich Hertz. You can read it. Originally it was written in German because Hertz was a German scientist. But the translated version in in the English translation is available under Google Books at this website, so you can go to them. Now let us consider the example. The example that we considered, similar example, we will consider now. Now what we have seen is expression for H. H is equal to j omega into jk plus 1 upon r p cross r cap into gr. This is the expression for H that we have seen. Similarly, expression for E also we have seen. I am not going to read it out, but the expression for E is given like this. Now what we will do is we are going to do some replacements in these two expressions for the example. The first replacement is P is equal to P vector P, or the dipole moment. P is equal to small p into capital G cap into exponential j omega t, because P is a time varying field. So for considering the time harmonic nature, we are writing P is equal to P vector is equal to amplitude of P or magnitude of P into z cap, it is oriented along z axis, into time variation is of the form exponential j omega t. Why we are taking exponential j omega t? Because as I told you, all these will be real. So real value of exponential j omega t will be cos omega t. So for cos omega t, instead of cos omega t, we are writing exponential j omega t. And so the advantage of writing in exponential form is it makes mathematics or analysis simple. So therefore we are writing exponential j omega t instead of cos or sin. Actually, ultimately we will go back to cos and sin. Okay. So if we do that, then the Green's function, time dependent Green's function, time independent Green's function is exponential minus jkr by 4 pi r. Then the time dependency will be of the form exponential j omega t. Therefore, g at t time dependent Green function will be of the form exponential minus jkr by 4 pi r into exponential j omega t. That we can write, there are two exponential terms. So exp minus jkr, exp j omega t, that will be actually exp of minus jkr plus j omega t. So that will be in the numerator, denominator will be 4 pi r. Then use the Euler formula. So using Euler formula, we will get 1 by 4 pi r into cosine of kr minus omega t plus j sine of kr minus omega t. So this much we get. Okay. And then we'll come to this part. J omega into jk plus 1 by r, that is equal to j omega into jk is jj is minus 1, so minus omega k plus j into omega by r. So that part we get. So that replacement we will make. Then the third replacement we will make is j omega into jk plus 1 by r into Green's function, time dependent Green's function, that will be equal to 1 by 4 pi r. That will remain as it is. Then in the time dependent Green's function, cosine of kr minus omega t minus j sine of kr minus omega t, that will remain as it is. Then what we will get, jk plus 1 by r. Now jk plus 1 by r is minus omega k plus j omega by r. So this part we will write in this manner. Then we will take the real part of this. If we take the real part of this, the real part will be p into omega into minus k cos kr minus omega t plus sin kr minus omega t by r. This is the real part of this part. And then the real part of 1 by epsilon 0 jk plus 1 by r into grt will be p into k sin kr minus omega t plus cosine of kr minus omega t by r. So these things you can do easily. Simple algebraic manipulations. So I am not deriving this. You can do these simple algebraic manipulations easily. So we are going to make these replacements in the expressions for electric field and magnetic field. If you do these replacements, then the electric field becomes ER is equal to ER is equal to P into K times sin KR minus omega T plus cosine KR minus omega T by R into 3R R dot Z minus Z by 4 pi epsilon 0 R square plus PK square R cross Z cross R by 4 pi epsilon 0 R cos of KR minus omega T. So this is the expression for ER. Similarly, expression for HR will be P omega into minus K cos KR minus omega T plus sin KR minus omega T by R into Z cross R by 4 pi R. Now remember, what is this P? P is the dipole moment, which means this is Q into DL or Q into DL. So that is what is P. Okay. Now we are going to use some simple things. Z cap. Z cap is equal to, Z cap is in the Cartesian coordinate system. Convert that into spherical coordinate system. So Z cap will be R cap cos theta minus theta cap sin theta. Similarly, R cap, once we know what is Z cap, then take the dot product of Z cap with R cap. So R cap dot Z cap will be cos theta, because R cap dot theta cap is equal to 0. So R cap dot Z cap will be cos theta. Then find out what is Z cap cross R cap. So Z cap cross R cap will be equal to minus T cap sin theta, because R cap cross R cap, that will be 0. Then minus theta cap cross R cap, that is minus T cap. So minus theta cap cross, because theta cap cross R cap is T cap. So minus theta cap cross R cap is T cap minus T cap. So Z cap cross R cap is equal to minus T cap sin theta. Okay. Then R cap cross Z cap cross R cap. All these terms are used in E and H. Therefore, we are finding it out. So R cap cross Z cap cross R cap is equal to R cap cross minus T cap sin theta, because Z cap cross R cap is minus T cap sin theta. Now R cap cross T cap is equal to theta cap. So this will be minus theta cap sin theta. Now put these values in the expressions for E and H. If you put these values in the expression for E and H, then ER will be, then ER, which means the R component of the electric vector E, this will be this value, E into K sin KR minus omega T plus cosine KR minus omega T by R into 2 cos theta by 4 pi epsilon 0 R square. Now look at this term. This term has a multiplication of 1 by R square, which means this term is dropping faster than 1 by R, which means this is not contributing to the radiation. So ER, so radial component of the electric field, does not contribute to the radiation. For a Hertzian dipole, radial component of the electric field does not contribute to the radiation. Then we'll come to the theta component. E theta is P K sin KR minus omega T plus cos KR minus omega T by R into sin theta by 4 pi epsilon 0 R square minus p k square sin theta by 4 pi epsilon 0 r cosine of kr minus omega t. Now look at the first term. It has sin theta by 4 pi epsilon 0 r square, which means the first term is dropping faster than 1 by r. So the first term is not contributing to the radiation, that is contributing to the near field. The second term is pk square sin theta by 4 pi epsilon 0 r cosine kr minus omega t, that is contributing to the radiation. Next is h phi. H will not have any other component, it will have only the phi component. So h phi is equal to this value, p omega into minus k cosine of kr minus omega t plus sin kr minus omega t by r into sin theta by 4 pi r. Now if you look at the second term, it has sin kr minus omega t by r, that is multiplied by 1 by 4 pi r. So the second term is dropping faster than 1 by r. So the second term does not contribute to radiation. It is contributing to the near field. So only the first term is contributing to the radiation. So now we have seen which are the parts which are contributing to the radiation field, which are the parts which are contributing to the near field, that we have now found out. And the component of the electric field and the magnetic field, that also we have found out. And we saw that the radial component of the electric field does not contribute to radiation, only theta component contributes. In the theta component, there is a part for near field, there is a contribution to the far field. Similarly, for the magnetic field, theta component is 0, radial component is 0, phi component has two terms. The second term is for the near field and the first term is for the radiated field. Now based on this, what we discussed, let me give you a homework, so that in the radiation zone, the fields for a Hertzian dipole can be expressed as E is equal to P by 4 pi j omega mu exponential minus jkr by r sin theta theta cap. This I have already discussed, but you have to do this. Next, H is equal to P by 4 pi jk exponential minus jkr by r sin theta phi cap. Now if you compare these two, you can easily see that eta 0 h phi is equal to E theta. This you can see easily from this. And if you compare these two, you can see sin theta is common in both the terms. Exponential minus jkr by r is common in both the terms. 1 by 4 pi is common in both the terms. P is common in both the terms. Only j is common in both the terms. Only difference is omega mu by k. So taking care of that, you can see eta 0 into h phi is equal to E theta. Now why it is h phi and E theta, you can see E has only theta component, therefore that is E theta. H has only phi component, therefore it is h phi. So this is a homework given to you. Please work out this homework. Then I will come to something which is conforming the radiation. If we consider this example, then let us conform the radiation. As you know, the Poynting vector, time averaged Poynting vector for a time harmonic field, we find out the time averaged Poynting vector, that is 1 by 2 real part of E cross H star. We have found out the expressions for E and H. So put those expressions for E and H. So it will be 1 by 2 P by 4 pi whole square into j omega mu exponential minus jkr by r sin theta theta cap cross, and then H star will be minus jk exponential jkr by r. Why minus jk? Because minus jk is a complex conjugate of jk. Similarly, why exponential jkr? Because exponential jkr is the complex conjugate of minus jkr. So it is exponential jkr by r sin theta phi cap. Now you know theta cap cross phi cap is equal to r cap. So that will be r cap. Now sin theta into sin theta will be sin square theta. In the denominator we will have r square. numerator exponential minus jkr into exponential jkr will cancel out. So that will leave us 1 by 2 into p by 4 pi square into omega mu into k into sine square theta by r square into r cap. Now if you look at the right hand side, the right hand side does not contain any j term, which means it is a purely real thing. P is real, 4 pi real, 2 real, omega real, mu real, k real, sine square theta is real, r square is real. Therefore, S is real. So S is real valued. So that is one conclusion that we draw. If we find out what is S, the conclusion that we find is S is real. Then the second conclusion that we find is S is directed along the radial direction. So radially outward, S is radially outward. So S is radially outward and S is real. That you can see here in this animation. What we are doing is we are showing we have a dipole, infinitesimal dipole, and that from that dipole the field is propagating outward. So energy propagation, you can see energy propagation. Look at the bottom, the projection of the energy propagation onto the xy plane. If you look at the xy plane, you can see that it is expanding, going out radially. So S is going out radially and this S is real value. So these are two things that we understand. Now let us find out what will be the radiated power. So this confirms that it is radiating. Since it is real, so it is radiating. Power is real. S is power density. So power is real. Power is real means actual power you are getting in the far field. So it is radiating. So now let us find out what is the radiated power. S is power density. Therefore integrate it over the area. So PF in the far field, so PF will be equal to integration S dot dA, which will be 1 by 2 into P by 4 pi into omega mu k into dA is integrated 0 to 2 pi over pi, 0 to pi over theta. So 0 to pi sine q theta d theta. Integrate this. Integration will give us simple expression 1 by 2 P by 4 pi square omega mu k, those will remain as it is. 0 to pi integration will give us 2 pi and the 0 to pi integration gives us 4 by pi. So put that PF is equal to omega mu k by 12 pi into P square. So the power is, total power is real power. Total radiated power is real power, and the power is dissipating. Since it is real power, so it is dissipating. It is independent upon R, so it does not depend at what distance you are from the source. Once you are in the radiated field or in the far field, it does not depend on R. So integration over a sphere of larger radius will give you the same real total power as over a smaller radius in the far region. Then this is called the radiated power. PF is called the radiated power. So what we consider up to now is for the far field, E theta and H field. Now consider the near field. Let us consider the near field. In the near field, what will happen? H near field. NF stands for near field. So in the near field, the general field expressions will be valid at any distance from the Hertzian dipole. That is point number one. Point number two, these are important in some applications, as I told you, one probe. So these are important in some applications. And for understanding this, for example, if you want to understand what is the input impedance of the dipole, we have to understand that. So to understand that, we require the electric field component and the magnetic field component. Now the electric field components, E near field and the E near field theta and E near field R, they are in phase. But they are in phase quadrature with the magnetic field component H in it. We'll see now that we'll see now. So H and F field, so they will be in the phase quadrature. If the electric field and magnetic field, they are in phase quadrature, then which means that the power is reactive power. If they are in phase, then the power is not reactive, it is dissipating. And if it is they are in phase quadrature, they are reactive power. So let us try to do this numerically. H and F is equal to P by 4 pi exponential minus jkr by r square sin theta phi cap. E and F, NF means near field. This is minus j eta P by 4 pi k exponential minus jkr by r cube sin theta cap, then minus j eta P by 4 pi k exponential minus jkr by r cube cos theta r cap. Now compare these two, H and F and E and F. They are in phase quadrature. E and H are in phase quadrature. So there is energy interchange between these fields with time. Since they are in phase quadrature, there will be energy interchange between H and E. So at one instant of time, the electric field will be stronger, or there will be all fields will be electric field. So all power will be stored in the electric field. So they are strong near the dipole, close to the maximum charge region. Then at another instant, so a quarter period later from this instant, the energy will be stored in the magnetic field. So from electric field, it is transferred to magnetic field. It will be stored in the magnetic field, primarily close to the center of the dipole, where the current is maximum. So now let us find out the near field power, S and F. This will be 1 by 2 E theta NF H phi NF star R cap minus E R NF H phi NF star theta cap. Now we know what is E theta NF and what is E R NF, what is E phi NF, what is H phi NF. So from that we can find out the power. S and F will be minus j eta by 2k p by 2 pi into 1 by r to the power 5 sin q theta r cap minus sin 2 theta theta cap. Now look at this has a term j. So this is imaginary power density, which means this power is not being consumed or radiated. So this gives rise to a standing wave. If you have a imaginary power density, that is giving rise to a standing wave instead of a propagating or traveling wave, which is associated with radiation. Propagating waves or traveling waves are associated with radiation. This is a standing wave. So since this is a standing wave, as you know, standing wave is storing energy. So this will store energy as in any reactive device. Reactive device means as in capacitor or inductor. This is going to store the energy. The reactive component of antenna is shown in input impedance. Input impedance, as you know, impedance Z is equal to R plus Jx. It has a reactive part X. For the antenna, it is Zin, which is equal to Rin plus Jxin. This Xin part is the manifestation of the stored energy. Because of the stored energy, you get Xn. So the real part of the input impedance gives you the power that is being radiated by the antenna. The imaginary part is the stored energy. Then we will come to the concept which is called Radian Sphere. Many times people neglect this, but try to know what is this. Start with the radiation power density. As we know, the radiation power density, this exists everywhere in the space. Once you have a Hertzian dipole, everywhere in the space there will be a radiation power density because of the Hertzian dipole. This power density, the radiated power density, passes through the near field. What happens in the near field is, the power in the near field dominates the power, radiated power, but it passes through the near field. The radiation power density passes through the near field. Okay. The distance of maximum power radiation, where there will be maximum power radiation, that will start in the, as you have discussed, in the zone where the near field becomes weaker and the far field becomes stronger. That is the point where they are equal. So near field and far field become equal. From that point onward, the far field will dominate. So therefore, at that point, K into R is equal to 1. K into R is equal to 1 means R is equal to, from that we can find out R is equal to 1 by K. K is equal to 2 pi by lambda, so R is equal to lambda by 2 pi. So if you are going a distance lambda by 2 pi from the Hertzian dipole, from that point onward, you will get the radiated field, but up to the point lambda by 2 pi, the reactive power will be dominating. So at R is equal to lambda by 2 pi, the reactive power will equal to the radiated power. Beyond that, the radiated power will dominate. Below that, the reactive power is dominating. So interior to this radius, R is equal to lambda by 2 pi, that part is containing and the reactive power, or that is the zone which is the near field. Okay. So this region is called the Radian Sphere. So R less than lambda by 2 pi is called the Radian Sphere. I think we'll stop here. The rest of the part I have sent you as in the notes. The rest of the part is not important from your examination point of view, but if you are interested in programming, if you are interested in animating the electric fields or the fields, etc., then that part is there. So we'll stop here. Maybe I will discuss that if you want. I will discuss that part. I will just show you how to do that. But that is available in your notes. You can refer the notes. If you have difficulties, you can ask. Otherwise, we will stop here for today. Then we will discuss. Let's get